January 15, 1965. Mesabi Range Iron Mines, Minnesota. The engineering wisdom from Detroit's most advanced automotive engineers would never fully capture what they witnessed that bitter winter morning. American mining trucks, operating with electrical systems that defied everything modern automotive technology said was necessary for heavy equipment reliability. Through the sub-zero wind and grinding of massive iron ore operations, identical Unit Rig M-85 Lectrahaul trucks moved 60-ton loads with mechanical simplicity that seemed primitive to visiting automotive specialists. No complex computer systems, no sophisticated hydraulic controls, no constant software updates. Yet they operated with consistency that modern haul trucks could not match. In Detroit's advanced manufacturing facilities, automotive engineers required dozens of electronic control modules to manage a single heavy-duty truck. Each system demanded specialized diagnostic equipment, constant firmware updates, and technician training that cost thousands per worker. Most carried maintenance schedules that required weekly interventions. The mining trucks were operating with electrical philosophy the automotive industry had abandoned decades earlier. Ward Leonard motor control, basic DC generators, simple resistance-based speed regulation, maintenance procedures any worker with basic electrical knowledge could perform in brutal mining conditions. 60 years from their original installation, the most enduring heavy equipment revolution in American industrial history was still revealing itself. Not in advanced computing power, not in sophisticated electronics, but in the systematic simplification that connected electrical reliability in ways modern engineering had forgotten was possible. The January morning brought temperatures that made steel brittle and froze hydraulic fluid solid, but the Mesabi Range iron mines never stopped. 40 million tons of iron ore moved through Minnesota's frozen landscape each year, feeding America's endless hunger for steel. The ore lay buried beneath permafrost that could snap shovel teeth like matchsticks, yet every day brought the same relentless demand from Pittsburgh's blast furnaces and Gary's rolling mills. Steam ruled the mines with absolute authority in 1895. Massive steam-powered hoisting systems dominated every major operation, their 15-foot booms swinging tons of ore with mechanical precision that European-trained engineers had perfected over decades. The bigger and more complex the steam system, the more American progress it represented. Steam shovels required dedicated teams of specialists. Steam locomotives demanded full-time engineers, firemen, and maintenance crews who understood the intricate dance of pressure gauges, water levels, and coal-burning efficiency that kept the massive machines operational. The mining and scientific press published detailed technical specifications that became gospel for mining superintendents across Minnesota. Steam pressure equaled American industrial superiority. Each steam locomotive generated enough power to move 30-ton loads, but operating costs averaged $3.20 per ton hauled. The mathematics seemed acceptable when measured against the proven reliability of steam technology that had built America's industrial foundation. Winter revealed steam's fundamental weakness with brutal clarity. Boiler explosions killed workers when pressure systems failed under extreme temperature stress. Ice formed in steam lines, blocking the flow of pressurized water that powered the massive machinery. Each breakdown required hours of warm-up time and careful pressure building before operations could resume. Minnesota's mining superintendents accepted these challenges as the inevitable cost of industrial progress, trusting European engineering wisdom that had powered manufacturing success across the Atlantic. The breakthrough appeared in 1893 through an unlikely partnership between Harry Ward Leonard, a Cincinnati-born electrical engineer, and General Electric's mathematical genius, Charles Proteus Steinmetz. Leonard's Ward Leonard system represented radical simplification rather than mechanical complexity. Instead of steam's 47 interconnected components, Leonard proposed direct current generators connected to motors through simple electrical resistance controls. 3 heavy-duty switches, 2 60-horsepower motors, basic electrical connections that any worker could understand and maintain. Steinmetz provided the mathematical foundation that transformed Leonard's practical insights into engineering reality. His calculations proved that electrical current could be controlled with the same precision as steam pressure, but without steam's mechanical complexity and temperature sensitivity. General Electric committed resources to mining applications, promising operational advantages that would revolutionize ore extraction throughout Minnesota's iron ranges. The first test at Susquehanna Mine destroyed Leonard's credibility within 48 hours. The electric motor burned out completely, leaving 30 tons of ore stranded underground while steam engineers worked through the night to restore normal operations. Steam advocates declared immediate vindication of their proven methods. Electricity belonged in city streetlights and factory illumination, not in America's mining operations where mechanical reliability meant the difference between profit and bankruptcy. Operating costs mattered more than theoretical innovation when mining companies calculated quarterly returns for Eastern investors. Steam systems generated measurable results through established maintenance procedures and replacement part availability that electrical systems could not match. Every mining superintendent understood steam technology's requirements and limitations. Electrical systems represented unknown risks that threatened production schedules and worker safety in environments where mechanical failure could trap men underground. Leonard faced the engineering community's collective skepticism with characteristic mathematical persistence. He redesigned motor specifications to handle mining conditions that no electrical system had previously encountered. Dust, moisture, temperature extremes, and constant vibration demanded electrical components built to industrial standards that exceeded anything General Electric had manufactured for urban applications. The partnership with Steinmetz provided crucial technical credibility that Leonard's practical experience alone could not establish. Steinmetz translated complex electrical theory into operational advantages that mining engineers could understand and implement. His equations proved that electrical motors could deliver consistent power output without the warm-up periods and pressure building that steam systems required. Electrical energy could be transmitted instantly across long distances, eliminated the need for on-site fuel storage and the specialized crews that steam operations demanded. Minnesota's mining industry watched Leonard's second attempt with intense interest. If electrical systems could prove themselves under real mining conditions, the operational advantages would transform ore extraction economics throughout the Mesabi Range. Lower operating costs per ton hauled, reduced maintenance requirements, elimination of boiler explosion risks that killed workers and destroyed expensive equipment. The financial calculations seemed almost too promising to believe. Electrical power could be generated at distant facilities and transmitted to mining operations through simple copper wire connections. No coal transportation costs, no water supply requirements, no specialized crews for boiler maintenance and pressure monitoring. The operational independence that steam advocates claimed as their greatest advantage might actually belong to electrical systems that could restart instantly after power restoration. Leonard understood that lasting innovation required more than theoretical superiority. American mining demanded proven performance under conditions that destroyed most mechanical systems within months. His electrical motors would need to operate continuously for years, not weeks, before the industry would abandon steam technology that had built fortunes throughout Minnesota's iron ranges. Leonard rebuilt his electrical system with obsessive attention to the mechanical realities that had destroyed his first attempt. The partnership with General Electric provided access to manufacturing capabilities that individual inventors could never achieve, but Leonard insisted on designing every component specifically for mining applications rather than adapting existing industrial motors. The breakthrough insight emerged through systematic elimination of mechanical complexity rather than addition of sophisticated controls. Traditional steam systems required intricate mechanical linkages to convert boiler pressure into locomotive motion. Throttle controls, pressure regulators, valve timing mechanisms, and speed governors created dozens of potential failure points that demanded constant adjustment and maintenance. Leonard recognized that electrical resistance could replace all mechanical speed controls with 3 heavy-duty switches connected directly to 60 horsepower direct current motors. No mechanical governors, no pressure valves, no complex linkage systems that broke down under mining conditions. The mathematical elegance appealed to Steinmetz, but Leonard focused on operational simplicity that ordinary workers could understand and maintain. Each electrical switch controlled current flow to the motors with precision that steam throttles could never match. Full power, half power, or quarter power settings provided all the speed variation that mining locomotives required. Any worker who understood basic electrical connections could operate the system without specialized training in steam pressure management or mechanical valve adjustment. General Electric's manufacturing capabilities transformed Leonard's theoretical design into industrial reality. The dedicated mining motors featured reinforced housings designed to withstand constant vibration and dust exposure that destroyed standard electrical equipment within weeks. Improved copper windings handled temperature extremes that caused conventional motors to burn out during Minnesota's brutal winter operations. Each motor assembly weighed significantly less than equivalent steam engines, while delivering superior torque characteristics for heavy ore hauling. The first successful test occurred at Wabigon Mine in 1900, where Leonard's electric locomotive demonstrated operational advantages that steam advocates could not dispute. The Ward Leonard system hauled 30-ton loads using only 2 operators, compared to steam's requirement for 5 specialized crew members. No boiler meant no fireman. No coal storage meant no fuel handler. No pressure monitoring meant no dedicated engineer. The electric locomotive started instantly without warm-up periods and maintained consistent speed regardless of load variations that caused steam engines to lose power on steep grades. Operating cost calculations revealed the decisive advantage that would transform mining economics throughout the Mesabi Range. Leonard's electric system cost $1.80 per ton hauled compared to steam's $3.20. The 43% cost reduction occurred immediately without requiring operational changes or specialized maintenance procedures. Electric motors ran continuously for months without stopping, while steam systems demanded daily maintenance and frequent repairs that interrupted ore production schedules. The MAP. Underground applications proved even more revolutionary than surface locomotive operations. Electric trolley systems replaced mule-drawn carts that had moved ore through underground tunnels since the earliest mining operations began. Miners nicknamed the electric locomotives juice motors for their instant responsiveness and reliable operation in conditions where steam systems could not function effectively. Underground steam operations required extensive ventilation systems to remove dangerous gases and heat that electric motors did not generate. Maintenance requirements demonstrated electric systems' fundamental operational superiority over steam technology. Steam locomotives required daily inspections of boiler pressure systems, water levels, coal quality, and mechanical linkages that connected dozens of moving parts. Electric motors needed occasional brush replacement and basic electrical connection maintenance that any worker could perform with simple tools. The 73% reduction in maintenance hours translated directly into increased ore production and reduced labor costs. Leonard's success attracted attention from mining superintendents throughout Minnesota who calculated the financial advantages of converting from steam to electrical power. No water supply requirements eliminated the need for complex pipeline systems that froze during winter operations. No coal transportation costs reduced operational expenses and eliminated fuel storage facilities that required fire protection and specialized handling equipment. No specialized crews meant fewer workers and reduced payroll expenses that improved profit margins for mining companies competing in volatile ore markets. The electrical independence that steam advocates had questioned became electric systems' greatest competitive advantage. Power generation occurred at distant facilities where coal could be burned efficiently under controlled conditions with professional operators who specialized in electrical generation. Mining operations received consistent electrical power through simple copper wire transmission that eliminated on-site fuel handling and boiler operation complexities. Word spread rapidly through Minnesota's mining community as Wabigon Mine's operational results validated Leonard's engineering claims through sustained performance rather than theoretical promises. Electric locomotives operated reliably through winter conditions that disabled steam systems for days. Instant restart capability after power interruptions meant mining operations resumed immediately rather than waiting hours for boiler pressure building and system warm-up procedures. By 1905, Ward Leonard electric systems operated throughout the Mesabi Range as mining companies converted their locomotive fleets to electrical power. The proven operational advantages convinced conservative mining superintendents, who had initially dismissed electrical innovation as impractical. Experimentation. Steam's mechanical complexity could not compete with electrical simplicity that delivered superior performance at lower operating costs. The transformation occurred through gradual adoption rather than sudden conversion, as mining companies tested electric systems on secondary operations before committing to full-scale implementation. Each successful installation provided operational data that supported Leonard's engineering claims and demonstrated electrical reliability under actual mining conditions. The mathematical precision that Steinmetz had calculated proved accurate in practical applications, where theoretical advantages became measurable operational improvements. Mining engineers who had spent decades mastering steam technology acknowledged electrical systems' fundamental superiority through direct operational comparison rather than engineering theory. Electric motors delivered consistent power output, regardless of weather conditions or fuel quality variables that affected steam system performance. The operational simplicity that Leonard had designed into his Ward Leonard controls made electrical systems accessible to workers without specialized technical training in complex mechanical systems. The underground revolution began where steam had never successfully ventured. Beneath Minnesota's frozen surface, mining operations extended hundreds of feet into ore deposits that required constant transportation of materials through narrow tunnels, where steam locomotives could not operate effectively. Mule-drawn carts had moved ore through these underground passages since the first mines opened, but the animals struggled in conditions that grew more challenging as mining operations expanded deeper into the earth. Leonard's electric trolley systems transformed underground mining with technological elegance that eliminated biological limitations and mechanical complexity simultaneously. Electric motors generated no exhaust gases that required extensive ventilation systems to protect worker safety. No heat production meant underground temperatures remained manageable without expensive air circulation equipment that steam operations demanded. The instant power delivery that characterized Ward Leonard's surface systems proved even more valuable in underground applications, where consistent transportation schedules determined overall mining productivity. Miners embraced electric locomotives with enthusiasm that surprised conservative mining superintendents who had expected worker resistance to unfamiliar technology. The juice motors earned their nickname through operational characteristics that made underground work safer and more efficient. Electric locomotives started instantly without warm-up periods that delayed shift changes and transportation schedules. Consistent speed control allowed precise coordination of multiple underground operations that steam systems could not achieve through their mechanical throttle controls. The elimination of specialized crews revolutionized underground labor organization throughout the Mesabi Range. Steam operations required dedicated engineers and firemen who understood complex mechanical systems, but contributed nothing to actual ore extraction or processing. Electric systems allowed ordinary miners to operate transportation equipment with minimal training while focusing their specialized skills on ore identification, extraction techniques, and safety procedures that directly improved mining productivity. Underground maintenance requirements demonstrated electric systems' decisive operational advantages over any mechanical alternative. Steam locomotives needed daily mechanical inspections, lubrication of dozens of moving parts, and constant monitoring of pressure systems that could fail catastrophically in underground environments. Electric motors required occasional brush replacement and basic electrical connection maintenance that miners could perform during routine shift changes without disrupting transportation schedules. The financial calculations convinced mining companies throughout Minnesota to accelerate their conversion from steam to electrical power. Underground electric systems eliminated the need for specialized ventilation equipment that steam operations required to remove dangerous gases and excess heat. No fuel transportation into underground areas reduced fire hazards and eliminated storage facilities that occupied valuable space needed for ore processing equipment. By 1907, electric trolley systems operated in every major underground mining operation across the Mesabi Range as word spread through the mining community about operational advantages that translated directly into improved profit margins. Mining superintendents who had initially viewed electrical systems as experimental technology now recognized Ward Leonard controls as proven industrial equipment that delivered superior performance under the most challenging operational conditions. The network effect accelerated adoption as mining companies discovered that electrical standardization created operational efficiencies beyond individual system performance. Maintenance crews could service electric equipment throughout multiple mining operations using identical tools and replacement parts. Worker training programs prepared miners for electric system operation across different mining companies, creating a skilled workforce that enhanced electrical systems' competitive advantages over steam technology. Underground operations revealed electrical systems' fundamental compatibility with mining expansion that steam technology could not match. As mines extended deeper into ore deposits, electric power transmission through copper wires maintained consistent performance regardless of distance from surface-generating equipment. Steam systems lost pressure and efficiency as mechanical linkages extended through longer underground passages, limiting mining operations to areas within practical steam transmission distances. The operational independence that electrical systems provided became particularly valuable in underground applications where mechanical failures could trap workers and halt production for extended periods. Electric motors restarted instantly after power interruptions without requiring complex pressure-building procedures that steam systems demanded. Emergency backup power systems could maintain essential underground operations during electrical outages, providing safety margins that steam technology could not offer. Leonard's engineering insight proved most valuable in underground applications where mechanical simplicity translated directly into worker safety improvements. Electric locomotives had fewer moving parts that could fail suddenly and cause accidents in confined underground spaces. No boiler explosion risks eliminated the most dangerous aspect of underground steam operations that had killed miners throughout Minnesota's mining history. The productivity improvements exceeded mining companies' initial calculations as electric systems enabled operational coordination that mechanical systems could not achieve. Multiple electric locomotives could operate simultaneously on synchronized schedules that maximized ore transportation efficiency throughout underground tunnel networks. Steam systems required sequential operations that created bottlenecks and reduced overall mining productivity. Technical standardization across the mining industry created competitive advantages that individual companies had not anticipated when they initially adopted electric systems. Replacement parts became readily available as multiple manufacturers produced compatible electrical components for Ward Leonard systems. Technical expertise developed throughout the mining workforce as workers gained experience with electrical equipment that operated similarly across different mining operations. The transformation occurred most dramatically in underground applications where environmental conditions favored electrical systems' operational characteristics. No combustion byproducts meant cleaner underground air quality that improved working conditions and reduced ventilation costs. Consistent temperature control eliminated the heat stress that steam operations created in confined underground spaces where worker comfort directly affected productivity and safety. Mining engineers recognized that electrical systems had fundamentally changed underground operations through technological capabilities that steam power could never duplicate. The instant responsiveness, mechanical simplicity, and operational reliability that characterized Ward Leonard systems proved particularly valuable in underground environments where equipment failure could have catastrophic consequences for worker safety and mining productivity. Underground electric systems demonstrated conclusively that Leonard's engineering philosophy of elegant simplification created operational advantages that complex mechanical systems could not match through additional complexity or increased power output. American mining had discovered that technological superiority emerged through systematic elimination of failure points rather than addition of sophisticated mechanical components. The Mesabi Chief Mine represented American industrial ambition at its most audacious scale. By 1920, the operation had evolved beyond simple ore extraction into a massive industrial complex that processed 12 million tons of iron ore annually. The installation demanded technological solutions that exceeded anything Leonard's Ward Leonard systems had previously attempted. Mining superintendents required equipment capable of moving ore at rates that would satisfy steel mills consuming unprecedented quantities of raw materials for America's post-war industrial expansion. Leonard partnered with General Electric's engineering teams to design the largest Ward Leonard installation in American mining history. The centerpiece would be an 8 cubic yard electric shovel with a 90-foot boom powered by direct current motors that delivered precision control at massive scale. The engineering challenge required scaling Ward Leonard principles from 30-ton locomotive operations to 1,200 ton per hour ore extraction without compromising the mechanical simplicity that had made electric systems successful throughout Minnesota's mining operations. The electric shovel represented technological evolution rather than revolutionary change. Leonard's fundamental insight remained unchanged. Electrical resistance controls could provide precise power management for any scale of mining operation without requiring complex mechanical linkages or sophisticated control systems. 3 heavy-duty switches still controlled motor operation, but the switches now managed electrical current flowing to motors 10 times more powerful than the original Ward Leonard locomotive systems. Construction began in January 1920 with General Electric manufacturing custom electrical components designed specifically for the Mesabi Chief installation. The motors featured reinforced copper windings capable of handling sustained high current operation under conditions that would destroy conventional industrial equipment. Each motor assembly weighed 3 tons but delivered power equivalent to steam systems, requiring 5 times more space and 10 times more operational complexity. The boom assembly demonstrated American engineering's ability to combine massive scale with electrical precision. 90 feet of steel structure moved with mechanical accuracy that steam-powered shovels could never achieve through their hydraulic and mechanical control systems. Electric motors responded instantly to operator commands without the pressure-building delays and mechanical linkage adjustments that limited steam shovel productivity during continuous operation cycles. Installation required 6 months of careful electrical system integration as Leonard's team coordinated power transmission, motor control systems, and mechanical interfaces that connected electrical innovation with traditional mining equipment. The Ward Leonard control panels occupied a small building adjacent to the shovel operation, containing the same basic 3-switch design that had proven successful in locomotive applications but scaled to manage electrical current flows, measured in hundreds of amperes rather than dozens. The first operational test in August 1920 exceeded every performance prediction that mining engineers had calculated. The electric shovel loaded 1,200 tons of ore per hour, tripling the output rate of the most efficient steam-powered equipment operating elsewhere in Minnesota's mining operations. The precision control allowed operators to fill railway cars with mathematical accuracy that reduced spillage and maximized transportation efficiency throughout the entire ore handling process. Workers adapted to electric shovel operation with surprising ease despite the equipment's massive scale and unprecedented power output. The same operational simplicity that characterized smaller Ward Leonard systems made the giant electric shovel accessible to experienced mining equipment operators without requiring extensive retraining or specialized technical education. 3 switches still controlled all power functions regardless of the enormous scale of mechanical operations those switches now managed. The economic impact transformed Mesabi Chief Mine's competitive position within Minnesota's mining industry and established new productivity standards that other mining operations struggled to match. Operating costs per ton extracted dropped to 42 cents compared to steam systems that averaged $1.60 per ton. The cost advantage occurred immediately without requiring operational changes or maintenance procedures more complex than the basic electrical system maintenance that mining crews had mastered during the previous decade. Reliability proved even more impressive than productivity improvements as the electric shovel operated continuously for months without mechanical failures that interrupted production schedules. Steam-powered shovels required daily maintenance, frequent repairs to pressure systems and mechanical linkages, and periodic complete overhauls that shut down mining operations for weeks. The electric shovel needed occasional brush replacement and routine electrical connection maintenance that workers could perform during shift changes without stopping or extraction operations. The installation attracted visitors from mining operations throughout North America as word spread about operational capabilities that seemed almost impossible to achieve through any mechanical system. Mining engineers traveled from Canada, Mexico, and South American operations to observe electric shovel performance and evaluate Ward Leonard technology for their own mining applications. The demonstrations consistently impressed visitors who had expected electrical systems to sacrifice reliability for increased productivity. Power consumption calculations revealed another decisive advantage as the electric shovel consumed electrical energy more efficiently than steam systems used coal to generate equivalent mechanical power. The mathematical efficiency occurred through elimination of intermediate energy conversion processes that characterize steam operations. Electric power flowed directly from distant generating plants to mining equipment without the energy losses inherent in coal combustion, steam generation, and mechanical power transmission that reduce steam system efficiency. March 1921 brought the most severe test of electrical system reliability when a nationwide railway strike disrupted electricity supply throughout Minnesota's industrial operations. Mining companies lost electrical power for 3 weeks as utility companies struggled to maintain generation without coal deliveries that powered most electrical generating plants. Steam advocates declared ultimate vindication of their technological philosophy, arguing that mining operations required complete independence from external power sources that electrical systems could never provide. The power outage revealed electrical systems' fundamental dependence on infrastructure beyond mining companies' direct control. Electric shovels, locomotives, and underground trolley systems went completely dark, while steam operations continued using coal reserves that mining companies maintained for exactly such emergencies. Steam advocates argued convincingly that American mining required technological independence that electrical systems had sacrificed in pursuit of operational efficiency and cost reductions. Mining superintendents faced difficult decisions about long-term technological commitments as the strike extended beyond initial predictions. Some operations began planning conversion back to steam systems that promised complete operational independence regardless of external power supply disruptions. The 3-week shutdown cost Mesabi Chief Mine nearly $2 million in lost production, while steam-powered competitors continued operating at reduced capacity, but maintained continuous ore extraction throughout the electrical power crisis. Leonard watched his technological revolution face its greatest challenge through external circumstances beyond any engineering solution's capability to address completely. The electrical dependence that had created operational advantages now threatened to become a fatal weakness that would destroy electrical systems' competitive position throughout American mining operations. The railway strike's conclusion in April 1921 revealed electrical systems' most decisive operational advantage when power restoration occurred throughout Minnesota's mining operations. Electric shovels, locomotives, and underground trolley systems restarted instantly as electrical current flowed through copper transmission lines, while steam operations required days of complex preparation before returning to full productivity. Boiler pressure building, system warm-up procedures, and mechanical component inspection created operational delays that extended the strike's economic impact far beyond the actual power outage duration. Mining superintendents discovered that backup power generation transformed electrical dependence into operational independence that exceeded steam systems' capabilities. Portable diesel generators could maintain essential electrical operations during future power disruptions without requiring the massive infrastructure investments that steam systems demanded for complete operational independence. A single backup generator could power multiple electric systems, while steam independence required individual boiler systems for each piece of equipment. The recovery period demonstrated electrical systems' fundamental compatibility with rapid operational scaling that steam technology could not match. As demand for iron ore increased throughout the 1920s, mining companies expanded their electrical installations without the extensive infrastructure development that steam systems required. Additional electric shovels needed only electrical connections to existing power transmission systems, while steam expansion demanded new boiler facilities, coal storage areas, and water supply systems for each additional piece of equipment. Leonard's engineering insight proved most valuable during the expansion period as Ward Leonard control systems scaled efficiently to manage multiple large electric shovels operating simultaneously at individual mining sites. The same three-switch control philosophy worked identically whether managing single electric locomotives or coordinating multiple 1,200-ton-per-hour shovels in integrated mining operations. Steam systems required individual operators and specialized crews for each piece of equipment, creating labor coordination challenges that electrical systems avoided through operational simplicity. The long-term reliability data accumulated throughout the 1920s and 30s validated Leonard's engineering philosophy beyond any theoretical predictions. Ward Leonard electric mining systems installed between 1900 and 1920 continued operating into the 1960s with the same motors, the same basic controls, and the same three switches that had characterized the original installations. Routine maintenance replaced worn brushes and updated electrical connections, but the fundamental system components operated reliably for decades without major overhauls. Steam system replacement cycles revealed the decisive economic advantage of electrical longevity as mining companies calculated total cost of ownership over extended operational periods. Every steam system installed before 1925 required complete replacement by 1940 due to boiler failures, mechanical wear, and maintenance costs that exceeded the equipment's productive value. Steam advocates' claims of operational independence proved economically irrelevant when the systems themselves could not maintain reliable operation for more than 15 years. The financial calculations accumulated over 40 years of operation demonstrated electrical systems' overwhelming economic superiority through sustained performance rather than initial cost advantages. Electric systems averaged 60 cents per ton, moved when calculated over their complete operational lifespans, including all maintenance, replacement parts, and power consumption costs. Steam systems averaged $4.20 per ton when replacement costs and specialized crew requirements were included in long-term financial analysis. American mining companies recognized that electrical innovation had fundamentally transformed industrial operations through systematic elimination of complexity rather than addition of sophisticated technology. The Ward Leonard system succeeded because Leonard had reduced steam's 47 potential failure points to basic electrical connections that ordinary workers could maintain with simple tools and elementary electrical knowledge. Mechanical simplicity created operational reliability that complex systems could not achieve regardless of their theoretical engineering sophistication. The workforce transformation proved equally significant as mining companies discovered that electrical systems required broader technical skills rather than specialized expertise in complex mechanical systems. Workers learned basic electrical maintenance procedures that applied across all electrical equipment, creating operational flexibility that steam systems could not provide. Steam operations required specialized boiler operators, pressure system experts, and mechanical linkage specialists whose skills applied only to steam technology. Technical education evolved throughout Minnesota's mining industry as companies established training programs focused on electrical system maintenance and operation. Community colleges developed electrical technology curricula that prepared workers for mining careers while providing technical skills applicable throughout American industrial operations. Steam system expertise became obsolete as companies abandoned mechanical complexity in favor of electrical simplicity that workers could master quickly and apply broadly. The network effects accelerated throughout the 1940s and 50s as electrical standardization created industrial efficiencies that individual companies had not anticipated during initial adoption decisions. Replacement parts became commodity items, available from multiple manufacturers, reducing maintenance costs and eliminating supply chain dependencies that had characterized specialized steam system components. Technical expertise developed throughout the workforce as workers gained experience with electrical systems that operated identically across different mining operations and industrial applications. Leonard's engineering legacy extended far beyond mining applications as Ward Leonard motor control principles influenced electrical system design throughout American industrial operations. Steel mills, manufacturing plants, and transportation systems adopted electrical motor controls based on the same resistance-based speed regulation that had proven successful in Minnesota's mining operations. The mathematical precision that Steinmetz had calculated for mining applications proved equally valuable in industrial contexts, where precise motor control determined productivity and operational efficiency. By 1960, the Ward Leonard systems installed during the early decades of electrical adoption continued operating reliably, while newer electrical technologies incorporated Leonard's fundamental insights about operational simplicity and mechanical elimination. Advanced electrical systems featured sophisticated electronic controls, but the underlying principle remained unchanged. Electrical resistance provided precise motor control without complex mechanical linkages or specialized operational expertise. The technological revolution that began with Leonard's 3 switches and 2 motors had transformed American industrial operations through systematic simplification rather than increasing complexity. Mining companies that had initially adopted electrical systems for cost advantages discovered that operational reliability and workforce flexibility provided even greater competitive advantages over extended operational periods. Steam advocates' warnings about electrical dependence proved irrelevant, as backup power systems provided operational independence while maintaining electrical systems' fundamental advantages in maintenance requirements, operational costs, and workforce training. American mining had learned that lasting technological innovation emerged through elimination of failure points rather than addition of sophisticated components, creating industrial systems that ordinary workers could operate and maintain reliably under the most challenging operational conditions that American industry could present.